Hi, in this video, we want to take a look at using iterative algorithms for forecasting with time series, specifically autoregressive models. All right, so if we look at a previous video, we figured out a lot of the details of the one step ahead predictions for an autoregressive time series model. Now, that's a very simple, mathematically simple way to do forecasting. It's great. Everything pencil and paper theoretically works out wonderfully, but there's a problem with it. That if I have a larger data set or a lot of terms in my time series model, then I'm going to end up getting matrices that are very, very large. And so we can have problems with memory and computation time if we want to take this approach for solving our time series. What we want to talk about in this video is how do we get around that? Well, what we're going to do, we're going to come up with iterative algorithms that are going to give us our solution without having us worry about such large matrices to do the computations. All right, now we are going to be taking some examples from time series analysis and its applications. That is the textbook for the course. Here are the authors of the textbook. Here's their GitHub page. And the textbook can be downloaded for free through UCF's library if you're a student. All right, so now let's go ahead and get into it. All right, so if I was doing things pencil and paper by hand and I didn't have too large of a model, I would be using matrices to work out the solution to my time series. But with real data, with real modeling that we would be using, it's probably not going to be feasible to have the computer handle that much memory and take that long to give us our solution. So what we're going to do, we're going to come up with recursive and iterative algorithms to give us our solutions. All right, so the first one we're going to talk about is the Durbin-Levinson algorithm. All right, so what we're going to do, the matrix form of the prediction equations is large gamma sub n times phi sub n is equal to little gamma sub n. Now, in the previous video, we talked about the prediction equations, which is, just by pencil and paper writing down what we're doing with time series and using the projection theorem, there's a little bit of linear algebra for you there, we end up getting this matrix equation. And of course, if this is a matrix equation and gamma is, big gamma is invertible, I just multiply both sides by the inverse of big gamma sub n. And from a pencil and paper point of view, I've got my coefficients like that. But it doesn't work that way in real life, because if I have a lot of data to be working with and or a lot of terms in that time series model, then this can be an unwieldy matrix to work with for the purpose of the computations. So let's come up with another way to approach this. All right, so first thing we're going to do, we're going to take a look at the mean squared one step ahead prediction error. All right, well, that's going to be the actual observed value that we haven't seen yet minus the value that we're forecasting the value with. So I observe in data points, I want to, in time, I want to predict the n+1 data point. So if I have a year of data, monthly data, n would be 12, and I would be attempting to predict next month value. And so then, we do the difference, that's the raw error, square it, and then taking the expected value will give us our mean squared one step ahead prediction error. Okay, so what we want to do, we want to solve this equation, and we want to have an estimate of our mean squared error at the same time. So how we're going to kick this off, we're going to take an iterative process. It's going to be recursive. I'm going to say that phi sub double 0 is equal to 0 just to kick things off. I'm going to set the mean squared one step ahead prediction error. So with just starting out here, I'm going to take gamma of 0, the variance of my time series, without doing the lag. So the auto covariance without the lag term, which is the variance. All right, so now what we're going to do for n greater than or equal to 1, we're going to use this equation here. So I'm going to take autocorrelation minus iterative value of the coefficient times autocorrelation lagged. And then on the bottom of my fraction, I'm going to replace this autocorrelation with a 1, and I have the same thing on there. So now this is going to give me a way to compute my coefficients in my model. Now, if you were to sit down and start working out from the previous video, the mean squared one step ahead prediction error, we would see that we're going to get this, the variance times the product of 1 minus our jth coefficient estimates squared, and then take the product of all of that. Now, for n greater than or equal to 2, what we're going to do is I'm going to take phi sub nk. Notice that here, the n and the k, the subscripts, do not necessarily equal each other. Actually, they don't ever equal each other. That's going to be phi n minus 1k minus that phi n that I mentioned a moment ago, phi n minus 1, n minus k, and we're going to let k go from 1 to n minus 1. Notice that it never actually gets to n. And so here, this is going to give us a formula for getting our coefficients. And this will give us our mean squared error. So let's run through an example of actually doing this. All right, so what we're going to do, we're going to go ahead and actually just start crunching this out. So in this process, I'm going to say that phi 1 is equal to the autocorrelation lag 1. So now that mean squared error, when I have 1 point of data and I'm trying to predict the second time interval, that's going to be the auto covariance at 0, the variance, times 1 minus phi 1 squared. All right, well, phi 1 squared, I know that is here, so I'm just going to plug that in. Okay, so now using the formula, when n is equal to 2, I'm going to take the formula, and remember that there's a summation here, but I'm so early in the algorithm, I don't have a lot of terms in the summation yet. So, and I'm only going to go so far with this since we're doing this kind of manually, but I'm going to take autocorrelation at 2 minus phi 1 autocorrelation at 1, replace this autocorrelation with 1, and then have take it and drop it into the denominator, and that gives me phi 2. Now phi 1, I'm going to use this formula here, and that's just phi 1 minus phi 2 times phi 1. Okay, and notice I can factor that if I would like to. Then my mean squared prediction error is going to be a product. Oh, this is an error. This should be a subscript 2, and this should be superscript also. So this should be subscripted. All right, so I know I'm going to take this, I'm going to multiply by 1 minus phi sub 2 squared, which I already worked out this part. So this gets slapped in for this, and you'll notice I get this result. And honestly, I could actually go straight to this. Just use this formula directly if I wanted to, instead of doing it iteratively. Now, for n equals 3, I'm going to play the same game, but you'll notice that now I've got more terms in that summation that's being involved in the subtraction. And then we just keep on crunching it out, just keep on crunching it out. And I could get direct to this if I wanted to. Okay, so let's use the Durbin-Levinson algorithm on some actual data. During a previous video, we used the partial autocorrelation function to determine that the REC time series, the recruitment time series, should be modeled with an AR2 model. So that's pretty short, pretty easy. You know, I can do this by hand if I want to, or I could drop it into a function in R. So let's do both, just to verify that this is correct. So the first thing I'm going to do is I'm going to load my data. Of course, this is a data set in the ASTSA package, which accompanies the textbook. Now, to do the actual calculation, to drop this into the function we're going to use in a moment, it wants a very specific format. To get it into that format for my autocorrelation function, I'm going to put my time series into the autocorrelation function that's in base R, but that's not quite the right format because the autocorrelation function is going to have more than just the raw values in there. It's going to have like the plot and other stuff. So I'm going to go ahead and with this $ ACF, I'm extracting the values. Now, this will also print the ACF plot for me at the same time. Now, for the actual function, this is not going to be in quite the right format. To get to the right format, I just convert it to a vector format. Boom, it's going to work out. And so here I can, when I do this call on this portion, this plot automatically happens, even if I didn't want it. Now, what I'm going to do, I'm going to take the vector version of the autocorrelation function output, and I'm going to drop it into the Levinson algorithm or function that is from the G-signal package. And I'm going to restrict the model to degree 2. And here we get our coefficients. We see we've got 1, we have negative 1.33, and we have 0.445. Okay? And here are some other values. We'll talk about those in future videos. Now let's do this manually. So this next code is me just sitting down and crunching it out. It's kind of ugly, but in the end, I'm going to try and get both outputs on the screen at the same time. When I'm all done, here I've gone through and manually computed this out. You'll notice I have 1.33 and I have negative 0.445 as my coefficients. Now, here you'll notice that I got the same values, but they're negative signs. Also, there's a 1 in here. And so when the G-signal package set up the equations for their, the autoregressive models that are solved by this, they have a slightly different presentation on the functions. You have to read the help documentation to know which version you want. Doing it manually, the way the textbook presents it, here are the coefficients. So up to sign change, it's the same thing. All right, so let's take a look at iterative solutions for the partial autocorrelation function. So the partial autocorrelation of a stationary process can be obtained iteratively as phi sub n. This is very nice that I know that my partial autocorrelation is going to correspond directly from a coefficient in this process. So it's like I'm working to get the coefficients out, and for free, as a bonus, I get the partial autocorrelation coming out at me. Now, using an iterative solution for the partial autocorrelation function and setting n equal to the degree of our autoregressive model, we're going to get to see that my best predictor for one step ahead when I have p observations is going to be exactly the equation of the process I have. And so this validates our approach. This lets us know that we're going in the right direction as we're approaching this. if I had, P points of data and I have an ARP model, then it makes intuitive sense that the right model for predicting the upcoming observation would correspond, exactly to the core aspect of my autoregressive model. Now you'll notice that the white noise term is missing because it's not part of the prediction process. All right, so one thing that this does for us further, this shows that for an ARP model, the partial autocorrelation coefficient at lag P is also the last coefficient in our model. So this shows that this term that we use that is a partial autocorrelation value is also, if I focus just on the Pth value of it, it gives me a coefficient in my model. All right, so let's look at the partial autocorrelation of an AR2 model. So previously, we used pencil and paper calculations to find the coefficients of an AR2 model. Well, something that we could do is that we could just sit down and start using the difference equations that we worked with previously to pull in some stuff. So what we want to do here, we want to pull in the new stuff we're talking about and the difference equations material in that video, and we want to bring it together and get more out of our analysis. So I'm going to take this equation, which is from our difference equations video. And so if I have an AR2 process, then the autocorrelation at step H minus the first coefficient times autocorrelation H minus 1 minus the second coefficient times autocorrelation, and that should be H, it is H minus 2. There should be an H in there, will be equal to 0. All right, well, if I recall calculations that I did previously about autocorrelation, I know that I have this going on also. So now I can take it and plug that back in. And if I go through and start plugging and chugging on the equations that we had previously, I can see that phi11 from our iterative process is going to be equal to phi1 divided by 1 minus phi2 of the actual model itself. So there's a difference in these fees. This fee, and this is not like fee as in money, this is fee as PHI. This is a much better fee than a fee you pay. Like, when you buy tickets from Ticketmaster or something like that, those crazy fees. All right, so here, this is the output of the iterative process. This is a coefficient from the actual process we're attempting to model. This is a coefficient from the time series process we're attempting to model. This is output from our iterative process. Well, it works out that if I crunch this out, if I go through, I did this by paper, by pencil and paper, by the way, I see that this phi22 ends up being the value I actually want it to be of the second coefficient. And we see that phi21 ends up giving us that first coefficient. That works out great. But wait, there's more. We see that the higher subscript values are going to be equal to 0 because I have an AR2 process. So they just cut off and I don't have to worry about them. This is awesome. This is great. And notice that, phi22 is equal to our second coefficient. All right, so now let's talk about going more than just one step ahead. So far, for making a prediction, we've only talked about taking our data and going one step forward. Now, that's great. That's important. That is like here and now, what do we do? But honestly, when I'm talking to stakeholders, when I'm talking to my boss, they want me to predict into the future at least 3 months into the future, at least 1 quarter going forward, probably more like 6 to 12. And so I need more tools. I need more oomph to get me there. So what I want to do, I want to get a predictor that can handle more than one step into the future, like M steps into the future. And so what we want to talk about is linear predictors for m steps into the future. Why are we doing linear? Because the math works out. We understand these theoretically well. Now, which linear predictor are we going to want? More than likely, we're going to want the best one. And in statistics, when I say best, that's minimum variance. All right, so what I'm going to do is I want to predict the n plus m point in time of the time series. I have n points of data. I've observed n points of my time series, and I want to go m steps into the future to make my prediction. All right, and this is how we denote it. I have n points of data. I want to go m steps into the future and make an accurate prediction. All right, and so as a linear process, I'm going to go ahead and just get some, I'm going to define my model to be a linear one of coefficients times lagged data. And these coefficients are going to satisfy the prediction equations if I sit down and start crunching them out. All right, so let's go ahead and sit down and crunch them out. If I take the expected value of n plus 1 minus j times the n plus 1 minus k observation, multiply by coefficients in my best linear predictor, then from the prediction equations, I know that this whole summation has to be equal to this expected value. All right, well, I look at that, and as long as we have zero mean of a stationary process, I know that those expected values are actually covariances. So let's go ahead and replace them with the proper covariances. If I subtract the subscripts from each other, I can see that the difference in subscripts is equal to k minus j. If I subtract the subscripts, I can see that this is the covariance for m plus k minus 1. Okay, so what we're going to do is we're going to set them equal to each other. That gives us new equations to work with. Let's go ahead and write those down, and let's put it in matrix format. So boom, now I have an equation in matrix format. Big gamma sub n is a matrix, and then phi sub n superscript m are the coefficients for m steps into the future, and gamma sub n is that auto covariance vector. Okay, so potentially what I could do, I could go through and I could solve this using matrix algebra, using systems of equations, using an inverse of big gamma. But I still have the problems of having a lot of data, having a lot of terms potentially in my model. That means I'll again have issues with computation time and memory. We want an iterative solution. And we're going to call it the innovations algorithm. All right, and so it's going to work out that the mean squared m step ahead prediction error, here is the mean square m steps ahead prediction error, is going to be equal to this equation of the variance minus the m step ahead covariance vector conjugating, not really conjugation, but on left and right, the inverse of big gamma sub n. All right, so that gives me the value, so I could work that out if I wanted to using matrix algebra. Now the innovations algorithm, when x sub t is a mean zero stationary time series, then the correlation of any two values between its, so take any 2 points in time, take the one step ahead difference between observed and predicted. Take the one step ahead difference between observed and predicted. It's going to work out that when the points in time are different, the correlation will be equal to 0. All right, so using this, we can derive the innovations algorithm, which is a homework problem. And so here we're going to show the use of it, not the derivation. All right, so we have an uncorrelated property, and we have the projection theorem to give us a direction on how to solve what we want to do. Now, notice that a point in time minus its one step ahead prediction is called an innovation. All right, so now let's do the one step ahead innovations algorithm. And so here is just a bunch of formulas. This is an iterative process. In real life, I'm not going to do this unless I really, really had to by hand. In real life, I would definitely program a computer to do it. I would prefer to go ahead and take someone else's work, like in R, and let R do all the work, or SAS or whatever. But here I have all my formulas. And so now let's do the M step ahead innovations algorithm. So after the one step ahead calculations are complete, so what first thing we're going to do is that we're going to compute one step ahead calculations for times 1 through n. Then the coefficients are obtained by continuing the iterations using the equations we just looked at. And we're going to use the formulas we just looked at to get the M step ahead forecast and mean squares error. And how do we do that? We're going to take the values we have here. So first step in this algorithm is that we're going to compute the M steps ahead, or sorry, the one step ahead predictions and errors for the data that we have. Then after we're done with that computation, then we're going to start using the M step ahead calculations that we have here and working out the details. Now in real life, I'm not going to do this by hand. I'm going to have a computer do it for sure. All right, now it works out that if I have a moving average degree 1 process, if I believe that that is the right model for my data, the innovations algorithm lends itself very well to predicting this particular moving average process. So let's go ahead and apply the innovations algorithm. And so here is my process. I know from several videos back that this is what my variance is going to be of the process. Here is my auto covariance with lag 1. Here's the, in general, because this is an MA1 process, the auto covariance is going to be equal to 0 for lags greater than 1. And we're going to kick things off with 0 as its starting point. And I'm going to take what I already know about the situation as my mean squared error. All right, and just using the formulas that we have, we're going to get this value, this equation for theta of n1. We know that theta of nj will be equal to 0 for larger values of j. And then here we see our mean squared error. And then here, this gives us our actual predicted value for one step ahead. All right, well, that's all I've got for you. Life is short. Do math.